Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang. Good afternoon, everybody. Do you hear my voice? Hello?
Yes, very clear, Mr. Radit.
Okay, thank you, Mr. Agus. So I think we have already both of the speakers here, Mrs. Irida Markja, PhD from Albania. Hello, Mrs. Irida. Sorry, can you turn on your mic?
Okay. Hello. Hello, everybody.
Hello, hello. And the second speaker is Mr. Agus Pramono, PhD. Hello, Mr. Agus.
Yes, I'm ready to begin.
Okay.
For the second keynote.
Okay, so we start this seminar online. The first speaker is Mrs. Irida Markja. I will introduce her to the participants here. So her name is Irida Markja, PhD from Albania. She got the Bachelor in Material Engineering at Polytechnic University of Tirana, Faculty of
Mechanical Engineering.
Mechanical Engineering, sorry. And then she continued to master degree, Master of Science in Material Engineering, also at the same university and faculty. And then in November 2016, she got a PhD tutel from Polytechnic University of Tirana, Faculty of Mechanical Engineering, and also Technical University in Freiburg Institute für Keramik, Glas und Baustofftechnik in Germany. So she has already several technical presentation, conference, and poster. I will not read all these extensive CV, I think. And also, she has already published some papers. Some of the papers were collaboration with Mr. Agus Pramono, I think.
Yeah.
So we can start the presentation. Please, Mrs. Irida, the screen is yours.
Yeah. Hello, everybody. I have opened my lecture. You can see it, I guess.
Yeah.
Okay.
Maybe it's still in the folder.
It's okay. Now?
Probably you should open your desktop and then you going to share screen, Irida. Thank you.
Mm-hmm.
And now?
Yes. Just please. Yeah. Okay. It's okay now. Go ahead.
Okay. So, hello again. My work or research that I will present today, it's related with or for surface engineering, the importance of surface engineering. And the study, it is focused on aluminum products in which we have used the samples or the products in a company in Albania to see the surface treatments and coatings of the importance of this application on aluminum alloys or products. As a definition, surface engineering we know as a treatment of the surface or metallurgical surface, also near surface regions of materials to allow the surface of the products to perform the functions, also to increase the properties of the materials, different from the bulk of materials. As a definition, we know from surface engineering, the properties of the materials increase to create a new surface or a thin layer with different treatments. We will see today anodizing as a process for aluminum products, which is a process which is adapted for aluminum chemical composition or aluminum as an alloy of aluminum, not aluminum as a metal. The desired properties or characteristics of surface engineering in let's say in field of surface engineering, components needs to improve the proper mechanical properties or try to improve the mechanical properties, also tribological properties. We can distinguish improving hardness of materials, but hardness meaning of on the surface of the materials, also as a tribological properties, improving the wear and also the corrosion resistance of the surface or related with the functional or functionality that the materials or the products we will use or we will do. Also controlling friction, improving the lubrication. It depends and from the geometrical or configuration of the products or related to aluminum products. Also, these processes underlining from surface engineering refer to some different post-processing to have an let's say to have a new surface layer or to create a new surface layer with the properties that we need to have long term or long use to have life cycle of the product different without treatment. And we will see what I have let's say trying to complete or conclude in this presentation, comparison between an aluminum alloy without treatment, without anodizing, and an aluminum product, the same chemical composition with surface treatment or an aluminum product with anodizing or created an oxide layer on the surface with a thickness which is related to the standard and to the industry, and to see the differences and to compare the properties. In our study, we have compared micro hardness and to see the results after comparison. This is the aim of this research and this presentation. Of my presentation also, it's not only my work, it's related and with my college, and a part of samples also, and our students had to work with difference or with let's say small study for diploma degree. And we will let's say introduce the influence that anodic surface treatments parameters has on created on the thickness of the layer and that created a different structure on aluminum products. And this is the layer that will have the function during the functionality or during the work that aluminum products or what they will use. The materials used in our study or in our research are from a company in Albania, Alumil company, and the series that we have worked it is the series from 6060 aluminum. The analysis of samples in our laboratory are performed, or we have performed, using optical microscopy, using a software Leica with a magnification 5000 for characterization of microstructure of anodizing layer or an oxide layer, which it is created after the process, engineering process. And after we have used the Vickers micro hardness for both samples or both groups of samples aluminum products. First group was non-anodized aluminum products from the company, and after we have seen and studied the micro hardness Vickers to compare the results when the aluminum products are anodized and they have a different layer on the surface, and to see the results of this research or this comparison. We know that aluminum and its alloys in our modern technology, let's say, they have more advantages, and they are, let's say, the world's second metallurgical product after steel, of course, due to some nice properties, and that the modern technology used them, especially low density and the good thermal and electrical conductivity. So due to the complex of advantages of the properties that alloys aluminum has, we or the industry or the technology use them, and from now we see that aluminum based alloys are very useful due to the properties that they offer. Well, surface treatments and coatings are applied to aluminum products to enhance their performance and to improve surface properties of final products, such the properties or typological properties that we said at the first slide. For sure that not only anodizing, but different types of surface treatments are applied. Since anodizing is one of the, let's say, best or more useful from the industry, because from the properties that the oxide layer achieved, it's very protective for the aluminum products, especially when these products have complex geometry during it depends on from the engineering technology. Also, they have a few decorative purposes with different colors, which is part of aesthetic in, let's say, in modern technology or in our days. And it's on common methods for superficial oxidation processes, and also it's carried out through anodic oxidation. It's a chemical reaction on the surface of aluminum products, which create the oxide layers. And the usability of aluminum products and aluminum alloys after anodizing as treatments or as an chemical treatments on the surface, it depends on the properties that the oxide layer achieved or oxide layer has during this process, because it depends on from the edited component or the chemical composition of aluminum alloys. Okay, as a surface treatment, it's an electrochemical treatment that increase an oxide layer, not too higher, but a thin oxide layer on the surface of aluminum, which will be the layer that will have the functional or we will has the responsibility for the life of the products. This is a scheme that let's say try to connect the processes of electrochemical treatment. The first section of our study is to evaluate the thickness of the oxide layer created after anodizing. First, we have carried out in the transverse section the samples of the anodized profile after polishing, after metallographic preparation on our laboratory. And observation for thickness estimation of the oxide layers were performed with 500 magnification and 1000 magnification metallographic microscope with optical microscope and micro hardness Vickers with 400 magnification. Metallographic preparation and the equipments, we actually have them in our laboratory and performed in material science and technology laboratory in our faculty. The second section is after evaluation of the thickness of the oxide layers, we have estimated the anodized layer, and our work or research, it is focused on the experimental part for estimating the thickness of the anodizing layer. And micro hardness Vickers we have performing on aluminum products with anodizing treatment on the surface engineering and in aluminum products without treatment. For sure, we have taken the samples in different elongation of the profile of aluminum in different section to see and the anodizing or to see then the process during the whole profile of aluminum, to see and the homogeneity of the process on different point and different section of the profile or of the surface engineering, because we should have an homogeneous layer or anodized layer or surface layer to have, let's say, a compatibility surface and to have the same properties in different point of the surface, because from this analyzing or from this process we will let's say or maybe the technology or the engineers are responsible for the analysis or from the work that they do, or or let's say from our research we will see results and we will perform it, or we will say it that okay, well, let's say 95% or 100% the micro Vickers, it's the same in different points or different part or section of the aluminum products. The series products use from 6060, and I have shown and chemical composition of the elements of this series of aluminum. The hardness or micro hardness Vickers, it is tested with 10 gram per force, and the force it is applied for 10 seconds in one indenter, or the indentation of the hardness, it is for 10 seconds for each measurement. Also, part of research or of the results, experimental work, it is focused on the thickness of the anodized layer, but in the meantime, maintaining the time for the anodizing bath, it's important for the results and for the properties that oxide layer will achieve after the experiment. These are samples that we have prepared, and are two plan or two section of the samples. And this is the microstructure and the layer, oxide layer, that it is created after anodizing process. And here is an indentation, one indentation, which we have taken from metallographic microscopy, optical one. And this is the whole oxide layer created on the material. And this is the profile or the aluminum product without treatments. This is the new surface created from anodizing process, which we will see that it's not the thickness, it's not the same during the whole, or let's say at this microstructure that we have taken at the moment with one indentation. So in all the elongation or all the part of the layers, we will make different indentation to see the micro hardness and to evaluate or to measure the mechanical properties for the samples or for the layer. The magnification for this microstructure, we have used 5000. As a conclusion, I have said, and from the definition of surface engineering, the anodizing surface of aluminum products based on the micro hardness measurement results higher hardness compared with the samples aluminum products without treatments on the surface. The micro hardness of layer anodizing, it is in the range from 400, 420 to 560, which is great compared with the chemical composition of aluminum, because we have for steel without treatment, or let's say a medium heat treatment, we have the hardness Vickers in the range of 400, 500 Vickers, comparing with the results of the aluminum samples without treatments. It's in the range for our profile from 50, 55 to 70 Vickers. So it's a very big difference between the materials before and after surface engineering or surface treatments. The conclusion we have shown, and in the graph, which compare and the homogeneity of the surface treatments, because okay, we achieved a higher hardness, but one of the biggest maybe problem or very critical issues is the homogeneity of the surface treatments. So for our research and in this presentation, we have shown for different distances 10 measurement, but for the whole article or paper has more results related to the micro hardness to see and the homogeneity of the oxide layer created on the aluminum surface. Okay, and comparing the results and after micro hardness analyzing, we have concluded that the characteristic of anodizing layer have improved for sure and increased their surface and product performance. Evaluation of micro hardness of the oxide layer with thickness 11 microns determined by our Leica soft provides that the anodizing efficiency increasing the hardness 8 times more versus the aluminum products without treatments or coating on their surface. This is the main, let's say, conclusion or results better to our research for the aluminum products that we have used and take from the company in Albania. The main references in our work, it was standard, American standard for surface engineering. Okay, I finished my presentation maybe a bit earlier than the time that I have it.
Okay, thank you, Mrs. Irida.
Thank you.
It's a nice presentation, and we are waiting for the question from the participants. In the meanwhile, maybe I have a question for you. In this research, have you examined the surface of the anodized aluminum from the top of the layer?
From the?
Have you examined the surface layer from the top, not from the cross section?
Yeah, we have analyzed from the cross section.
No, I mean from the top of the layer.
Yeah, you mean on the, okay, but can you repeat this?
As I remember, the shape of the oxide is, I think it's a hexagonal forms. If I'm yeah, it's the form of the oxide layer. It's hexagonal. If we examine the layer from the top of the top view. Have you examined this layer by maybe with SEM, for example?
Okay, our research, it is done in Albania, in Tirana, in my faculty, and it's important to analyze with SAM, but for the moment we do not have the equipment. So we have our research, it was focused and it's done with optical microscope performed with soft, so that we have it. Leica soft, also micro Vickers.
Okay, okay.
It's nice question, that nice work, but for the moment we do not have the equipment. So
okay.
I understand now the question, then you are right, but
so we have yeah, so we have one question from Mr. Bambang Wongso. What it's two questions. The first one is, what kind alkaline you use?
What kind of?
Alkaline. Maybe it's what kind of solvent?
Lithographic preparation.
For the anodizing, I mean.
For anodizing or for you mean for anodizing, or the question is for anodizing or for metallographic preparation?
I think it's for anodizing because it's alkaline. Yeah, for anodizing. Did you use alkaline solvent, or maybe you use another solvent for the anodizing?
Yes, but as I said at the beginning of our research, in this work or in our research or in this presentation, let's say, aluminum products we have taken from a company, and it was their part of preparation of anodizing process. And they wanted to, it was a collaboration between industry and our lab to see the surface layer and the anodic layer created from their parameters and their process. And in this presentation, I haven't, let's say, written the parameters of alkaline or what they have used. The part of the preparation of anodizing layer, it was of the industry in this research. but I can ask, and maybe I can have the email of the person that asked for the alkaline chemical composition.
Okay. So maybe for the next question, how long time you did the process? Yeah, I think it's
For anodizing,
how long the time for the anodizing process, I think.
is exactly the time for these samples. Maybe I will be wrong if I say, but it's less than 10 minutes, and it depends on them and from the geometrical profile that they yes or has or let's say cut, because our samples are taken from the whole profile. We haven't prepared different samples or small samples for the research. We have taken the whole profile in the industry and take different section. But it's less than 10 minutes.
Okay. So do we still have any question for the participants? Please write down your question on the chat room, and I will ask the question for you. So I think we don't have any question anymore. Sorry, we still have one. Still from Mr. Bambang Wongso. As your experience, what kind application advantage of this anodized for? So the question is, what is the application of this anodizing? What is the application of the anodized aluminum?
Yeah, the application is for the windows and for the doors in this, the profile that we have used, and also for part of the doors of the machine.
Okay. And maybe you can mention the advantage of this product.
Sorry, the advantage of the profile, or
no, the advantage of the product.
it is useful as a component, as a structural component, and they use it for windows, for doors. In which sense the advantages? The advantages is because they have, let's say, a long cycle of life. They do not has externation, or they do, especially they have a good, they do not have wear or consumption or corrosion without, so they are more strong as an with an anodic layer, depending of the aluminum without anodic layer. And especially in the countries with humidity, they has a long cycle, or as an advantages. It is the surface.
Okay. So maybe this is the last question from me. Even though there are many advantages of this anodized aluminum product, but of course there are still disadvantages of the anodized surface. So what is your opinion about this? for the anodized surface, is there any disadvantage during the process, for example, or during the application?
But during the application, I don't think so. That is an advantages, but having the anodizing process, these profiles for sure they will have better properties or complex properties. I think because maybe the question. I think.
Yeah. Okay. Thank you very much, Mrs. Irida Maksha, PhD from Polytechnic University of Tirana, Albania.
Okay, thank you.
Yeah, we are happy to see your presentation today, and once again we want to thank you for your kindness to join this online seminar.
Okay, and I also would like to thank you all for attending this presentation. And so I would like to greetings and Dr. Agus Pramono, because hello, and also to thank him for the collaboration in distance, but from our college, Claudian Doska.
Yeah, say hello for Claudian Doska.
Hello.
I miss him.
I really also would like to thank you because you have been during this year very helpful for us, and
Sure.
greetings.
Okay.
Okay.
So thanks again, Mrs. Irida. Have a nice day, and maybe one day we can meet again in another time.
Thank you.
Okay, bye.
Bye.
So we have seen the first presentation from Mrs. Irida. The last one is Mr. Agus Pramono, STMT PhD Tech. Okay, I will read his biography. His name is Agus Pramono, STMT PhD Tech. He worked at the Department of Metallurgy Engineering at University of Sultan Ageng Tirtayasa in Cilegon, Banten. He completed his bachelor degree at Mechanical Engineering Department, Merdeka University in Malang, and then he continued to the master degree at Department of Metallurgy and Materials, University of Indonesia, and then he got the PhD from Department of Materials Engineering, Tallinn University of Technology in Estonia. He worked in our department since 2007, and from his CV, he has many research experience and also publication in Indonesia and also abroad. So I think I will ask Mr. Agus to present his work this afternoon. So please, Mr. Agus.
Thank you so much, Mr. Aditya Tranggono, as our head of Department Metallurgy. First of all, I would like to thank for Committee of Seminar Series 7 on Metallurgy Material. This is a great program, great seminar, because we can create with some researchers from abroad. And then for my heart, this is a very, very great program. Okay, probably I will share my knowledge experience, but a little bit different with Dr. Iza Marja, because we are got the same slide of research, but it's a different basic science, I think. Okay, this at this moment we would like to discuss about my experience project in the research about repetitive press roll forming, or RPRF, as new method of shear plastic deformation. Okay, during 30 or 40 minutes, we would like to discuss about the term of material in shear plastic deformation, about basic science, about what kind of type of SPD, microstructure, and then it is important to know who is inverter of SPD. And finally, we would like to discuss about my novel of SPD, namely shear plastic deformation on repetitive press roll forming. And the last, we would like to discuss, we would like to talking about what the application in the SPD or LPRF. Okay, shear plastic deformation is a generic term describe a group of metal working in the technique involving very large strain, but typically involving of complex stress strain or high shear, resulting in high defect density and acquired ultra fine grain. So in here, I mean, this is scheme of kind pressure or force in the term of theory. We know that more small, more fine grain in the grain, so the tensile strength will get higher. Basically, for modulus elasticity, it is for create in the moving of dislocation. And basically, for the SPD, this obtain increased mechanical properties. For example, if we got aluminum series 1 till series 7, if we use SPD, so the mechanical property similar with steel or with another metal that get high properties. I mean, if we process aluminum with shear plastic deformation, so we will get to best or better mechanical properties, I mean. And as far as I know, between the yield stress and grain size, there's an effect. I mean, the finer grain for the SPD and the modulus elasticity influenced by stress, while the strain influence of the value of length of material when give a deformation load. And this is a kind of SPD. Principle of SPD, there were three kind of SPD. First is equal channel angular pressing. Second is high pressure torsion, and the last is accumulative roll bonding. You can see in here, this is two more force. I mean, for me, SPD, shear plastic deformation, is a collective of force more than one. If we compare with conventional process, metal forming, for example, we just get one force. For example, forming, we just get the pressure force. But if we use a cup, we got the two kind of force. First is tensile strength and compressive strength. For example, high pressure torsion, we got one press and one torsion in the up. on the dies. And accumulator rebonding, we use one for cumulative rebonding, press in compression, and then stack for plate in the sample. This is a kind of schematic silver plate deformation, cup, XPT, and ARB. In K engineering, I define a cup as a combination of tensile and compressive strength in the dies to produce a product with superior properties. You can see in the strain value here, this is same but different formula. This is that different for another process. For example, if we compare with the conventional process, I mean, if we use modulus elasticity, this is more high for mechanical purpose, and everything depend on cyclus. Cyclus, I mean, we should get more than one time of pressing or one time of roll. If we use more than one pressing till 10 pressing, we will get the best mechanical properties. Okay, this is a morphology of microstructure deformed by silver plate deformation. You can see here, this is a coarse grain. This is ultra fine grain. The mechanical properties of microstructure change during SPD. The process can be explained, illustrated in here. This is by aluminum, and this is by microstructure of composite. And this process is connected with removal of some defect, the grain boundary, I mean, here. And in the granular accompanied by relaxation of internal elastic stress. This is output stress. This is internal stress make some dislocation moving. And dislocation moving make transgranular dislocation. This is the new of theory, I think. By some researcher from Russia, like Ruslan Palik, or some researcher from UK, like Teknik Langdon. And the second step in characteristics of emergence of unbalance, I mean, if the grain will move, be smoother. So grain boundary migration with result of partial grain growth, and under abnormal condition, this is abnormal condition because too high pressing, too high more force. And finally, the third stage is connected with subsequent normal grain growth. If the model illustrated reflected here, from here, I mean, the processing SPD material depend of heating rate and time of different heating state in the process. In the figure, we will compare between aluminum and aluminum-based composite. This is different mechanism for moving of dislocation. This is important to know who is discovery of silver plate deformation. First is Professor Vladimir Segal. His discovery silver plate deformation, and second PM Bridgman is from USA, and the last Professor Nobuhiro Tsuji from Japan. And Ruslan Palik, he did research ECAP and SPT as well, like Professor Stephen Segal and Professor PM Bridgman. And here Teknik Langdon, it is got new idea of theory. He make experiment about superplasticity. If we combine composite with some metal and some ceramic, he know who did well. I mean, for the last experiment by Mr. atau Professor Teknik Langdon, he up just 1000% of superplasticity. It means he did research by aluminum, the properties similar with steel, and the elasticity similar with plastic. It is a great experiment. So for Mr. Aditya Trenggono, I hope someday next time we should invite him, Professor Teknik Langdon. It is great research, I mean.
Okay.
Is my ex-supervisor, Professor Lembit Komel, PhD Tech. He working in Tallinn Institute of Technology. and he got the experience as director Lulka Saturn Moscow, a manufacturing of military equipment. He is as a director, and he got so many experience about silver plastic deformation because between Professor Lamit Komel and Ruslan Valeb is very close for friend. Like me and Mr. Adit, very close for friend. Okay, this is a regime or standard equal channel armor pressing. For ECAP, have been determined for most metal alloy, but the studies for compaction of metal material composite powder are still rare. Sample for ECAP are commonly in the form bar or root here. The process can be applied also the plate sample or powder. On the figure in here, that's so a schematic model of ECAP. This is a ECAP procedure. We got dice or mold. Dice or mold has a channel that is bent under corner most commonly through the 90-degree in here. And for dimension, we should know about how many dimensions in the die. On beside picture, that you can see in here consolidation a cup for powder. You should make some capsule and using facility with content to parallel channel, namely a cap parallel channel. Me and Mr. Professor Lambit Komel did well in here. So we make some experiment and we got 3 journal in some publication journal. And for the parameter of die, this is important because that must be considered by a CAPTC process and developer reduce the restriction of conventional ECAP. It has been established that the optimal value of processing parameter leading to the large strain homogeneity in the cross section of the process billet till 100 degree. And displacement, I think it's better if we use free of displacement. Here, to produce variable mechanical properties and grain distribution, different ECAP ratio. So we got 4 route of ECAP processing. It is route E, route BE, BC, and route C. This is the depend on the use of material. I mean, for we use material composite, we should use route E. For steel, we should use route C. For composite or ceramic composite, we should use route BC and BE. So the route of ECAP processing distinguished by turning the sample under prefined angle between the pass, usually degree Celsius. How many times for rotate? It is depend on some material. So route A, for example, is free from is free from till here 2 or 3 times is depend on the material. And route A is free from rotation. During route BE, the sample turn alternative with the reverse direction, and under the angle degree Celsius in the route BC, the rotation in the rotate sample is conducted without reversing the direction placing by consecutivity process under 90 degree between each pass. In route C, the sample is rotated 180 degree between the pass. Combination of these routes are allowed as well. For example, combining BC and C, it is possible. I mean, it is possible to use more one route. And here we can see in this for aluminum pure and aluminum series 1 till series 7. This is mechanism of dislocation. So for accumulative roll bonding, is type of the SBD process where rolling a stack sheet material in use to increase the grain size, and generally nanometer, micrometer, or nanometer grain have higher strength than conventional material that have grain size large than a few 10 of micrometer. So the stack of material, we use some part of material, we should cut in some of different material, so we can get the accumulative roll bonding. During IRB process, shear strength built excessively by friction between roll and sheet with improved the grain refinement, and there were two conditions in the process. If the sample are without lubrication here, with lubrication as seen in the top right picture, then the grain structure is parabolic profile. This is a good condition because will increase the mechanical properties. In the sample without lubrication here, so the grain structure is parabolic and achieved during the first cycle with result of formation of single parabolic distribution axis in shear strength. Then the peak shear strength above surface. If sample are lubricant, it will change the dependent of mechanical properties and another properties. So rolling process parameter after the performance characteristic of the RB pressing. So the most important in parameter process, furthermore, several process variables such as up, down, and roll diameter material, reduction velocity of roll friction, and metal flow condition. So we can get some another part in here. Three condition. This is important to know because deformation behavior of sheet and quantifiably through combination of experimental rolling and finite element we were used for to know how many pressing occur in here. And additional cyclus 1, cyclus 2, cyclus 3 for IRB process will produce elongated coaxial grain resulting from strain hardening as shown in here in step 1, step 2 to step 3, which increase the hardness microstructural evolution during the IRB process, and the process in interface bonding are the most important factor in determining mechanical properties. So for the aluminum, we should get cyclus till 7 till 8 cyclus. But for the steel and another material, we should more than 10 cyclus of pressing. So this is another improvement of SPD combined by XPT and ECAP, I mean. For the next discovery and development SPD, I would not say much do because I think we don't have time enough for this discussion. But during the last 15 years, the SPD method have been developed rapidly. New methods simply by process or enable producing with superior properties. You can see here equal channel angular torsion. This is improved for composite as well, and also another method improved in China and in Korea, the name equal channel angular rolling or accumulative continuous extrusion. This is combined another method and another method. For example, equal channel angular rolling is combined by HAP and IRB, for example. And this is the last development in 2012 and 2010 in UK and in China. This is for accumulative press bonding in UK and in Kyushu University, continuous press extrusion. Hello, Mr. Adit, I still get time for this?
Yes.
Okay.
You still have time.
Okay, for application in industry, we got so many application, but it's not commercial. I mean, you know that mostly part component by silver plastic deformation is expensive. So that reason the SPD product per component is not commercial. For example, in A, we get piston produced by super plasticity. It is improved in Russia. And B, this micro gear from India. This is from Korea, Russia, and another part improved in another country. And for the military application, we get some part of helicopter, for rocket, for army helmet, for first army in this, because the product by silver plated deformation got high mechanical properties. This is for military application as well. Improve in AAV-7I1 amphibious assault vehicles for by system. This is created by equal channel angle pressing and accumulator throw bonding. This experiment research doing well by Japan and Germany. Also, NATO improved the Armata and tank T-15, and this is designed from Abraham and Battles tank. So this is mostly made from silver plastic deformation. In 2016, Russia success for making some part of MPV or car for military, mostly till 20 product improved by silver plastic deformation since 2016. This is a new method by me, improved in Tallinn University of Technology with my supervisor, Professor Lambit Komel. You know that by repetitive pressure forming, pressing is open die was at standard ARB, quite same with ARB, but different because in repetitive pressure forming, we add one press more. If we compare with ARB, ARB just get force from rolling, but in repetitive pressure forming, we got stress forcing for rolling and open diverging as well. So the first uniaxial pressing was carried without no lubrication, same with ARB, using approximately, if we use material composite, we use 50 ton hydraulic pressing, and then reduction same with ARB 15%. And during the second step, second cyclus, the reduction by rolling was performance strip preheat as well to make formability. Because for aluminum series 7, it's very difficult to pressing. So we use add heat treatment annealing. This process is capable reducing 1 till 5 millimeter, I mean, and I have finished trial for material RPRF by composite aluminum series 1 till series 7 and use ceramic silicon carbide and aluminum nanofiber as well. This is a simulation by my project. The first, based on description, theory, and result of ARB experiment, aluminum composite can be explained in this phenomenon microstructural evolution during the first cycle. So the part structure of ceramic and metal, I mean aluminum, so will part one by one and embedded in stack of aluminum here. So the second step of rolling, this is use higher temperature as well. So the produce of ultrafine grain, I mean, this is possible to get the grain till 1 or till 7 nanometer. Here, probably I will little bit use in Indonesia because this is my last experiment research grant with my colleagues in University of Indonesia. Today we would like to improve the material armor for car of military by repetitive pressure forming. In here, you know that this is by rolling, and we add by pressing. So we got the high properties till 1,200 tensile strength and total elongation till 50%. And for the formability, we use annealing temperature as well for the aluminum-based composite. So this is not easy to practice because we got the limitation for but for some material for some part of engineering, because this is a new method of pressing. So this is me and Professor Anne improve application of military technology in some laboratory in military in Indonesia. Okay, the last I would like to share my simulation with the finite element. This is simulation by ANSYS, new ANSYS. One is preheating for aluminum and input in Markov furnace for aluminum, and for the transfer of heat during 15 minutes, this get the radiation and heat improve in some part. We got some value of heat, and then the next step is forging process, open die forging. I mean till 25 ton, and some plate of aluminum. We got some distribute of thermal transition, and after we got 5 cycles, we reduce 50% of dimension, and for the deformation press, we got the ultrafine grain, and ultrafine grain we got high properties. This is a distribute of pressing in some part in here. We predict how many best the focus we will get by simulation. So thank you so much for your attention, and I reply for Mr. Aditya as a moderator. Thank you.
Okay, thank you very much, Mr. Agus Pramono. I just want to remind all the participants that you must complete the Google form that you can find on the chat room. You complete the Google form, and then we will send you the e-certificate by email. So please don't forget to complete the form. So for the first question for Mr. Agus Pramono, it comes from Mr. Akbar Vandito. What is the significance between the diffusion atom while the metal is compressed with two kinds of force, the tensile and compressive stress, with the temperature that used for doing SPD hardening?
Okay, thank you for the question. First of all, I would like to explain about the use parameter in SPD, especially in repetitive press roll forming. And the first, diffusion get by high press. For example, if we use more than tensile strength, I mean the ultimate press, so the atomic will move by dislocation and transcellular dislocation. After that, the recrystallization temperature will closer with more atomic and more get structure for that. And then if we know how to diffusion make some collaborate between atomic and atomic, so the high force, high pressing is can moving the index Miller. For example, for aluminium, the index Miller 111. So by high pressing, so aluminum will get 110, for example, for dislocation and make some diffusion. And for the temperature, I suggest use temperature less than dynamic recrystallization. For example, in aluminium, if we use temperature for process, we should get the temperature aluminium, I think 300 till 400, not much, not more, I mean. So if we want to get the best properties, the best material, so we should know ideal of temperature and pressing. As far as I know, for aluminum and composite, the pressing not much than 4,000 ton, and for the temperature not much than 400. Because I explained in some journal, if we use temperature to 400, so this is a cancel of distortion. I mean, it's not good for diffusion. Thank you, Mr. Adi.
Okay. The second one is from Miss Ii Nurul Hapsari. As I know, failure can occur for every process. From your method that you develop, what are the factors that can trigger the failure? How to deal with that fail process?
Yeah, I know what her mean. But the failure is complicated theory. I mean, so we should know about what kind of pressure in some part of material, because endurance limit for composite by SPD, for example, is not so easy to get long cycles. You know, if we use long cycles for material, I mean, if we use material, get material, and the material got the long cycles, this is not good for industrial, because it's not commercial. I mean, not commercial, because if we use a long time for endurance limit for filer, this is a bad condition in the market. But in the some theory, as far as I know, predict filer is by how many time we use operational in some part. I mean, for example, we try to make from spare part by RPRF, for example. If we use more than one force, so the structure will get the ultrafine grain. Ultrafine grain is better for application in some part. But if we use less than 100 two more of force, it is not ideal condition, because it is not good for diffusion. And the last, I think, for filer analysis in material composite by repetitive pressure forming, I cannot answer as much as possible, because it is quite new for manufacturing. This is maybe for suggestion for me to create the experiment to predict for filer analysis by repetitive pressure forming. This is quite good idea, I think.
Okay. The next question is from Yogi Anas. I'm very interested with method used for military. The question, what this method SPD can be help military from damage detected rudals?
Okay. We can see in slide number 15. Yeah. Number 15, we can see in here, just used by accumulative roll bonding, because for the bar, for the plate, this is quite good for accumulative roll bonding. If we use powder, if we use beside powder, this is just only accumulative roll bonding we can use. And for the process, we can combine with ARB and another conventional process, for example, a buckling process. This is to join process by accumulative roll bonding and another manufacturing process. So if we want to make some part of rudal, I think better if combined with ARB and another conventional process like RPRF. RPRF is combined ARB and conventional process. It should be tried for experience. I mean.
Okay. The other question is from Torik Safri, our students. How about the possibility for your method to be able to industrialize in Indonesia? Is it possible or not? Thank you.
Yeah, I think for the possibility is, I think so. But for the real condition, it's not so easy to apply RPRF in industry. For example, in Krakatau Steel or in Krakatau Bosco, because they had another standard for handbook, for example. You know, in some method of civil information, it is quite sufficient for standard. But in standard in international, it is not ready for that. It is not quite difficult to apply in the industry because as far as now, just for experiment, just for research in laboratory scale. For apply industry, we need some how to say? We need some parameter. We need some new equipment for applied in industry. Maybe we should be patient for waiting repetitive performing in applied in industry, I think.
Okay. I think it's we don't have any question anymore. It's a very good presentation from both of the speakers. I just want to remind the participant that we will still online 5 minutes after the end of the seminar, just to allow all the participants to complete the Google form, because the certificate will be sent to the participant who fill in the Google form. So we back to the two speakers. In my opinion, it's a good presentation from Mrs. Irina and also Mr. Agus. And as a metallurgist or materials engineer, or maybe the people who don't have any background in metallurgy or material, if we want to change the material properties, it's not necessary to buy or to change the material. The one way is to change the functional, the surface properties, as Mrs. Irida present today, for example, by anodizing. The bulk material is similar, the aluminum, but the properties of the surface change dramatically because the presence of aluminum oxide. And we don't have to change the material type. We just modify the microstructure of the metallic material, for example, by SPD, by severe plastic deformation. To my knowledge, the SPD is just it's a method to refine a grain size by applying force, for example, tensile or pressing by several times, for example, 2 or 3 or 5 times of rolling, forging, or etc. So that's the beautiful of the metallurgy and materials engineering. We don't have to buy the new one. We don't have to change the metallics, for example. Just modify the surface or modify the microstructure, and then we will get the new one with the better properties for the specific application. So that's my conclusion for this online seminar. I would like to thank you to both speakers, Mrs. Irida Markja, PhD, and also Mr. Agus Pramono, PhD, and also all the participants who have attending this online seminar. So thank you very much on behalf of the committee and also the department. I would like to sorry if there are something that you don't like during this online seminar. So I think we are at the end of this online seminar. Please fill in the Google form for the participant. And once again, thank you and see you at the other seminar. Thank you. Bye all.
Bye, Irida. Thank you so much, Irida. Thank you. Say hello for Claudian and all friends in Albania. Thank you so much.